All right, in this video, we're going to be going over theoretical versus experimental probability. So to start, we want to define what these two things are. Theoretical probability is defined as how likely an event is to occur. This is a prediction of an event if the number is repeated a large number of times. So what we've been doing throughout this chapter and this packet is we've actually been calculating theoretical probability. What should the probability be theoretically? This is what you expect to happen, right? Now, the way that we find theoretical probability is the formula that you have been using since the beginning of the packet, right? This reads that the probability of event A happening is equal to, well, the desired number of outcomes over the total number of outcomes. So pretty much what we've been doing when calculating the probability of a single event. That is theoretical probability. Now, I'm going to skip expected value and go to experimental probability so we can understand the difference between these two. So experimental probability, this is going to be after an experiment has occurred. So what this is the probability of an event, based on the outcomes of the experiment. This is what actually happened, right? So theoretical is what you expect to happen theoretically. Experimental is what actually happened, right? And we'll look at some examples here throughout this video. And that brings us lastly to expected value, right? So to calculate the expected value, what you're going to do is multiply the probability of an event times the number of trials. So for example, what we have here, if you want to find the expected value, in other words, to give you an example, if we were to draw a card from a deck 30 times, how many times would we get a queen, right? This would be the formula we could use. We could say the probability of the queen times, well, you have 30 trials, right? And this will hopefully start to make a little bit more sense as we start to look at some examples, okay? There is no real formula for experimental probability. It really is just the number of outcomes you had over the total. So with that being said, let's jump into the first example. It says a fair coin is flipped 10 times. Calculate each of the following. Now, it says calculate the expected number of heads, right? Well, if we pay attention to what is being said here, we can see that the coin is flipped 10 times. Okay, so what this represents is 10 trials or 10 flips. And if we're asked to calculate the following, how do I calculate the expected number of heads? We do so by finding the probability of flipping a head and multiplying by the number of trials, which we said there are 10 trials. So this would be how we find the expected number of heads. If we're looking at a coin, we understand that the probability of getting a heads is going to be 1 over 2. If we multiply that by 10, that would give us the expected value for 10 coin flips. This lets us know that 5 of those flips theoretically should result in heads, right? Which makes sense, right? Half of those flips should be heads. The expected number for tails pretty much is going to follow the same idea. We're looking at the probability of tails times the number of trials, which, like we said earlier, there's 10 coin flips, so 10 trials. Probability of flipping tails is the exact same probability of flipping heads, so we have 1 over 2 times 10 again, and this tells us 5. So the probability of flipping a coin 10 times, then we can say that we can expect to flip tails 5 times, all right? And then now we're going to look at, and we're really just paying attention to the vocabulary here, the wording in the problem, the expected number, that is your probability times the number of trials. Whereas we look at the next part here, it says the theoretical probability of flipping heads, right? So in theory, what will be the probability of flipping heads? Well, that would just be probability of flipping heads. It's just 1 over 2, right? There's a 1 out of 2 chance that we flip heads. That is our theoretical probability. All right, so just pay attention to the wording of the questions. Now, if we look at the next part of this example, it says the theoretical probability of flipping tails, right? Well, theoretically, our probability of flipping tails is, well, we have 1 desired outcome, which is tails, over the total number of outcomes, which is 2. So 1 over 2. Okay, and then we are looking at part E. Part E is going to be the last part of this example number 1. It says the experiment is completed and 7 of the flips were tails. What is the experimental probability of flipping heads? So now we're actually looking at the experimental probability, what actually happened, right? So if we are asked what is the experimental probability of flipping heads, the 7, well, that tells us 7 of the flips were tails, right? If we had 10 flips in total, that tells us that the remaining 3 flips were heads. And so if they ask us what is the experimental probability of flipping heads, well, probability of flipping heads, the experimental probability is what actually happened. How many flips did we get that were heads? 3 out of the total 10. So there it is. Your experimental probability for flipping heads for this particular experiment with the data that we're provided is 3 over 10. Okay, and so that in a nutshell is the difference between theoretical versus experimental. Just to summarize again, theoretical is what should happen. Experimental is what actually happens. So we'll do one more example here. We'll look at example number 2. It says an 8-sided die is rolled 24 times. Calculate each of the following. The expected number of times you roll a 7, right? To get the expected number, we take the probability of that event, so the probability of rolling a 7, and multiply it by the number of trials. Well, we can see here that we're rolling the die 24 times. So probability of rolling a 7 times 24. Well, if we're talking about an 8-sided die, we know that there's 8 total possible outcomes. And how many 7s are on that die? There's just 1. So the probability of getting a 7 is 1 over 8. Multiply that by the number of trials, 24. That would give us the expected number of 7s we can expect to roll doing this 24 times. If we multiply this, 1 over 8 times 24, that gives us 3. So that this makes sense. We are answering this question saying that the expected number of times you would roll a 7, we expect to roll a 7 3 times if we were to roll a total of 24 times. Okay, now we're looking at the expected number of times you roll an even number. Well, if we're looking at the 8-sided die, our even numbers are 2, 4, 6, 8. So expected number of times we roll an even number, we're looking at the expected number, so the probability of getting an even number times the number of trials, which is 24, right? So the probability of getting an even number, your numerator is the desired number of outcomes. We have 4 possible desired outcomes, so 4 over the total number of outcomes of 8. Multiply that by 24. Well, 4 over 8 simplifies to 1/2, and 1/2 times 24 gives us 12. So for part B, we can expect to roll an even number 12 times when doing this 24 instances. And then we finish up here with the theoretical probability of rolling a prime number. Well, looking at those prime numbers here, our prime numbers are 1, 2, 3, 5, and 7, right? And depending on how you were taught growing up, 1 isn't really a prime number, but I'm going to put it here because most of us grew up understanding that 1 is prime, okay? But we're going to not get into that topic in this video, but we'll run with these as our list of prime numbers for this die. And our theoretical probability would be the probability of rolling a prime number. This is theoretically what should happen. Well, if you look here, the desired number of outcomes we have is 5 prime numbers out of the total number of outcomes of 8. So 5 over 8 would represent the probability of rolling a prime number. And that brings us to the last part of our lesson for today, where it says the list below shows the outcomes of the rolls. So here's a list of the outcomes of the rolls of doing this 24 times, right? You can count every single number that we have here, and you'll end up seeing that this represents the actual results after conducting 24 rolls. So we understand there's a total of 24 here, right? So I'll just go ahead and write that. Total of 24 rolls. Now they ask us, what is the experimental probability of rolling a 1? Again, experimental probability is what actually happened. So let's take a look. How many 1s do we have? Here's a 1, here's a 1, here's a 1, here's another 1. So going through that list, the experimental probability of rolling a 1, well, we rolled a 1 4 times out of the total 24. So if you simplify that, 4 over 24, you can divide the top and bottom both by 4, giving us 1 over 6. So the experimental probability of rolling a 1 was 1 out of 6, right? And you'll notice that there are going to be times where your experimental probability is different than your theoretical probability, because that's just how life works, right? Not everything is going to go as planned. Not everything is going to happen theoretically as it should. Now, the last example here, part E, says, what is the experimental probability of rolling an even number? Right? Well, if we're looking at the even numbers, our even numbers are 2, 4, 6, 8 on this die. So we'll do this in a different color. Let's do this in blue. Highlighting our even numbers. 2 is even, 6 is even, 8 is even. We got even, 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 and even. Okay. And if I look at the ones that are not highlighted blue, I can see that those are odd numbers. So I didn't miss any. It doesn't look like I did. So what is the experimental probability of rolling an even number? Well, if we look at the highlighted blue numbers here, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We have 11 even numbers. So our probability of getting an even number is going to be, well, we had that happen 11 out of the total 24 times. So there's our probability of rolling an even number. Okay, and so that's going to be the end of our notes on theoretical versus experimental probability. Okay,